All right, everybody, thanks for joining us for this data structures and algorithms cohort. This is actually review session 2 for our course. This is going to focus on abstract data types and data structures. The other session that I will host later today is going to be all about the algorithms portion. So hopefully you can join that as well. All right, we're going to start our Kahoot. We've got 10 people or so in the room. There's another one, need to pass, love it. Let's get started. Happy to have you. The first question is on the board. You have a clock. Don't worry too much about the clock. It's just so that we can get through 24 questions today. It's not a real exam or anything. All right, which of the following data structures only stores homogeneous data elements? What's homogeneous means? It means it's the same type. So for instance, you can only set this up with integers or floats or I don't know, strings, booleans, whatever the case may be, arrays. That's right. For Python, we learned there are 2 limitations. There's first is that it is limited to homogeneous types, and the second is that you have to declare the size in advance. Otherwise, you're going to have some problems with that. All right, you get points for getting the answer right, more points for getting it righter, or not righter, right ahead of other people. Come on, righter. Question number 2. In a binary search tree, which node has to be the root node? A lot of questions on your exam, if I was designing the exam especially, would be about binary trees. There are lots of different binary trees. We primarily focus on binary search trees. So the answer to this is actually that any node can be the root. And we'll show you an example of that because you'd think it's the largest node. But the largest node, that's never going to be the right on a binary search tree. Okay, I just said that it could be any node, but in its fashion, if you're looking at a nice balanced tree, that's not going to be the case. So we're going to look at some examples of that. All right, Christina, you got the lead. Carrot, need to pass. You're going to have to do better. Come on. All right, here's a graphic here. I'm going to ask you, how many children does the root of the following BST have? BST is binary search tree. Previous questioners do, everybody answered ahead of time, so we didn't even run the clock out. Running out pretty fast though. Must be people counting. So what does this mean? It says, how many children does the root of the following binary search tree have? Well, you didn't even have to really do a lot of counting, because what is the rule for a binary search tree? A binary search tree, at most a node can only have 2 children. So when you looked at this, here's our root 50. Here are the children, 20 and 70. Those are the only children. When you go down to 5, 36, 64, 92, those are grandchildren. So make sure you know all of these vocabulary terms for binary search tree. Those are good, easy questions to ask. Way to go, Carrot, taking the lead. Vocabulary right here. In a binary tree, a blank is a node with no children. Leaf, exactly. Yeah. What is the height of the following binary search tree? Half a dozen slides or so that we're going to throw in as we go along here on some of these items. We'll be looking at those after the next question. So the height of the following binary search tree is 4, and most of you got that. Why? Because remember, if you only have 50, if you only had the root, the height of that would be 0. Your height is going to be as you're counting your lines. Remember what those lines are called? Your edges. So you're counting those. 1, 2, 3, 4. The maximum number of lines. That's how you're doing that. So you can't count the levels. 50 is a level, 20 and 70 is a level. Here's 5, here's 3, here's 4. Those are levels. But the height is 1 minus that. That minus 1, actually. All right, how are we doing? Great, doing great. All right, let's do one more question, and then we'll look at some slides. Which tree traversal method returns the nodes in ascending sorted order? I guess about half of you are going, what? What is this about? What does this mean to be reversing the trees? If you haven't joined our game already, please do. The information is in the chat bar. It's also at the bottom of our screen. You can head to www.kahoot.it, pin number 3521765. We'd love to have you. So we've had quite a few people join since we've started. It's called in order tree traversal. So let's do some PowerPoint slides now, right? What's the world without PowerPoint? So binary tree basics. Remember, each node has up to 2 children. Here's 40. Those are 2 children. Maximum, each node is going to have 2 children. Now, this is whether it's a binary search or something else. This is just binary tree basics at this point. Lots of different binary trees. The root is always called, it's always the top node. An internal node is a node with at least 1 child. So if you look at 30 has at least 1 child, right? A leaf is a tree with no children, so 25, 35, those. Parent, a node with a child is the parent. Ancestors include the node's parent, so on and so forth. So what are the ancestors of 25? That would be 30 and 40. So question, you can answer this in the chat bar. What about our root, 40? Is 40 considered an internal node? Do we have any thoughts on that? Think about what the rules are for that. Yes, it is considered an internal node because it does have at least 1 child. You see, it's got 2 children. If it was there by itself, well, then it would not. But yep, that's the rules for it. Tree depth, level, and height. The link from a node to a child is called an edge. So those are your edges. The circles, we're calling those nodes. So nodes and edges. A node's depth is the number of edges on the path. So here, when we're looking for the depth, we're looking for the depth to here. Well, the depth is 1. If we're looking for the height is going to be all the way down to the farthest possible one. So remember, a tree's height is the largest depth of any node. A tree with just 1 node has a height of 0. So if we only had 40, that's going to be 0. What happens if I add just one extra node down here? Does that change our height? Yeah, you bet. It doesn't matter if it's fully populated or if you just have a single node down here. It's still the maximum number to get to the farthest one. Be familiar with all of those. Here's our BST in order traversal. This is the idea so that you can get everything in ascending order. If we look at the pattern for the way this goes, it's going to start off at the farthest bottom left-hand node. And the algorithm says start there. You're going to do it. You're going to hit its parent, and then you're going to hit its right node. Then you're going to come up, and you're going to hit its parent and right node. You're going to come up. You're going to hit its parent. And now you have to go and do the right-hand side. So to go to the right-hand side, you need to back all the way down to the farthest left of it. So here you have 7050, parent, and right-hand node. So as you do that, you're ending up with 1125, 100, 201, 300. Come back over here, 750, 775, 925. So you're going to eventually get them all in ascending alphabetical order. Ascending order, alphabetical if you happen to be doing letters, I suppose. But there are some other tree traversals. I don't think they're covered on this particular exam. There's a nice graphic. You can screenshot this. The in order is showing you the same thing. If you're going to do it, this is the algorithm to do this by. If you were asked about a pre-ordered traversal, where you can see the way that's doing is you are starting at your root and you're working your way down. 7. If you're doing post order, how's that going to work? Well, now you're doing it kind of in a, well, various different orders. Level order traversal is probably the one we would be most familiar with, where you're just starting at the top and you're doing 1 and you're going across 2, 3, and then 4, 5, 6, 7. There's different reasons why you might use one over another. All right, so that's all I can tell you about binary trees for now. Carrot, still our leader. Emily, you've moved up. So y'all are doing super. Next up, let's ask about a priority queue. This would be implemented as a blank. What might you use to do this optimally? That's the word we want to do, the optimal. I throw that in there because, truly you can implement any of these things. Any of our abstract data types can be implemented based on top of an array. An array is sort of the end all be all, but it doesn't mean it's efficient. So even though you could do it with an array, probably not the way you want to do it. Instead, you would rather do this with a heap. We'll see why in just a moment. All right, true or false? That was an easy one for you. Most levels of a heap will be automatically sorted. What do you think? What do you call studied up on heaps? Oh, 50-50 split, a little more if you're wrong on that. Let's look at heaps. So what are we going to use a heap for? This is when you're looking for fast access to the maximum item. Remember the rule on a heap, this is still a binary tree, but not a binary search tree. On a heap, the only rule is that the highest priority is going to be on top. So whatever, we're just talking about a max heap in this case. If you want to know about a min heap, flip everything I'm saying upside down. Max heap, highest priority, 10 is going to be on top, and then the children will be lower than the parent. Children of those will be lower than their parents, so on and so forth. So that makes it where you've always got that top priority right on top. You can always just pick off the top priority and then reorganize everything for the next one. For this to work, when we are looking at this, here's an example. And I was talking about a max heap. So here we have 100. Here we have 40 and 50. You see those 10, 15, 50, and 40. You want to make sure as you're looking at this, you keep each side separate. Every time you go here, if you notice this bottom 50 is greater than this 40, but that's okay. It's less than or equal to its own parent. We're only looking at it from its parent side. We don't want to try and cross over. So that's the rule. Heapification, the way this works, is that we need to know how we are going to remove an item from it. And the rule for this is that we're going to start off by pulling the 100 and we're going to swap it with the farthest right hand element. So we would just do 140 pop. Okay, we switch places with them, and then we give you the 100 to work with. So you're really popping it at that time, at that point. But you have this 40 in place up top. That's not going to be right. So you have to do heapification, which says, check and see if you need to do some flip-flopping around, or you're going to percolate it down to the correct spot. So you would have a 40 here, and you'd say, is 40 greater than 40? Well, it's not, so we could leave it alone. But what about 50? Aha, okay, so 40 and 50 would swap places. Then you have 40 here. Is 40 greater than 50? It's not, so it's going to swap places with that one again. So that's the way that works. If you are adding a new element, and when you add a new element, you're going to add it to the farthest open spot. So if here we don't have anything open, so the next spot would be down over in this area. We'd add our new element, and then we're going to percolate up. We're going to be doing swapping until we're sure that it gets to where it needs to go. So lots of different things for heapification. Some good questions on that. Key point about binary search tree. When you have binary search tree, remember, left node is less than, right node is greater than. So that is important to keep in mind. With the heap, that's not the case. That's not the case at all. We don't have any rules about the left node or the right node being greater than or less than. The only rule is that they have to be less than the parent. Don't get those confused. All right, what is the underlying data structure for a dictionary? Dictionary, pretty good topic here. I don't really see the word dictionary used all that often. We're generally going to see hash table. And here's why, because your dictionary is going to be a hash table, but your hash table isn't necessarily going to be a dictionary. That's the way we want it to be. How does a hash table work? Well, it works with key value pairs. In the following dictionary example, which value is the key? Key value pair, when we think about this as an actual dictionary, are any of you here even old enough to know what the Webster's Dictionary is? That was an actual book. Okay. Did you use they listed in alphabetical order? You go look up a word and find out the definition. So in this case, your key is the word that you're looking up. The word you're looking up is is dictionary, and the value is going to be the actual definition. So name is the key, value is the definition. Let's ask you about hash collision. I would pepper the exam with hash table questions. This is a very good topic. I feel certain you're going to have questions about this on your exam. There are lots of definitions and there are some key concepts. Try and hit the ones that I think are most salient for you. Collision is when two different inputs produce the same hash output. It's when you're trying to put two items in the same bucket. Question works out really well. Tell me two ways that we can use to resolve a hash collision. Got a couple of PowerPoint slides to discuss this as well. Yeah, chaining and probing. Back to our slides here. So collisions. What is a collision? It's when an item being inserted into a hash table maps to the same bucket as an existing. When you do this, when this happens, you can resolve this with a couple different procedures. The first is chaining. Remember, your hash table in its most classic form is it's going to find a bucket and it's going to drop your item in it. It's going to drop that integer into the bucket. That's perfect. That's what we want. But we hash our values. It turns out we have an item in the bucket and we're trying to put something else. We have two options. The first is chaining. That means that instead of us having one value in there, we're now going to change that value from an integer to some sort of a list. We're going to have a list, and we'll have a list of integers there. Maybe one, maybe two, maybe we don't know. N. That's really what it is. It's N number. Alternatively, we have probing, and there are various different versions of probing. There's linear probing, there's quadratic probing, lots of things you can see. I think that kind of goes beyond the scope. Probing says it's going to look for an empty bucket elsewhere in the table. You've hashed it, and it looks like it's going to go in bucket 5. Bucket 5 has something in it. It says, oh, well, let's look at bucket 6. 6 has something in it. What about 7? Oh, okay, well, we'll go ahead and put it in bucket 7. we do want to think that there is this concept of empty since start bucket. We don't want to use a used bucket. So if we do that, 5, we're trying to put it in 5. 5 is taken, 6 is taken, 7's empty, but 7 did have something in it beforehand. We don't want to use it. We want to go for 8 or 9. We want to generally want to find a bucket that has been empty since start. Talk about calculating the hash value. We demonstrate in this course using the modulo operator. The modulo operator is nothing more than finding the remainder when you're dividing two numbers. And typically when we do this for our course, we're only working with double-digit numbers. You don't need a calculator, especially since we typically use 10 as our divisor. So what are we doing with this? We have our 10 elements. Remember, elements are numbered from 0 to 9. 0 to 9. So it's 10 element hash table is created. We're looking to hash a value of 64. So how do we do this? We'd say 64 divided by 10. Well, it's actually 64 modulo 10. So that means 64 divided by 10 equals 6 remainder 4. We don't care about the 6. We're only looking for the remainder. That's our modulo. So that means we're going to find bucket 4 and we're going to drop our 64 into it. That's it. That's how we calculate it. We got a couple extra minutes. So I'm going to point out, why do we care about collisions or probing? Because this goes back to our when we're talking about big O efficiency, calculating our big O runtime complexity for our algorithms. When we are hashing this value, as we do 64 modulo 10, that is an O of 1 operation. It takes us that blip of time. It's not going to get any more complex as we add things to it. So we calculate that for whatever amount of time it takes, that O of 1 time, and we drop it into the bucket. When we're searching for it, same thing. We're searching for it. We said 64 modulo 10. Hey, we need to just look at this bucket 4. But when we end up with our probing or a linked list, we don't have that O of 1 anymore, because instead we're now having to iterate through our list. We have to, oh no, we've got a list with 10 items, 100, 1,000 items, whatever the case is, n number of items. So it becomes that O of n operation. Same thing if we're probing. It's not here. Oh, we've got to probe to the next one, the next one, the next one, the next one. So ideally we have a hash table with lots of buckets to satisfy what we're looking for. Is that very likely? Probably not. Probably going to have some kind of collisions. Need to pass. Moving right up the list there. Way to go. All right, that's the last PowerPoint slide. So the rest of our game will move right along. We're on the second half of it. Let's talk about in which bucket would the value 76 be stored in a 10 element hash table. Looks like I covered that one question early, didn't I? Expect everyone to get this. Oh, look at that. So 76, how are you going to compute this? That's 76 divided by 10, and we just want the remainder. So that's 7 remainder 6. Remember, in math here, if we're doing double digit with divided by 10, we're just looking at the last number. That's all we're looking for. So it's going to be 6. The following ADTs are ordered and indexed. Abstract data types. That's the question. I've kind of considered changing this question, but we'll go with it anyway. The reason I think it's a little bit tricky is because it does say list, and it's not a linked list. When we're talking about our data structures, the very basics of this, we have our linked list, singly linked, doubly linked. Those are not indexed. But our Python, our built-in list, which acts very much like an array or a dynamic array, is indeed going to be ordered and indexed. A queue is not. A stack is not. Dynamic array or the built-in list, not a linked list. Please do not confuse that. That is a characteristic that's very specific about linked lists, is that they are not indexed. You do not have that positional index like you do, where you could say my array element 13. Again, an O of 1 operation. With a linked list, you would have to iterate all the way counting to get to the 13th one. All right, a queue works using the blank principle. Principle is this. We've got a lot of four-letter words here. LIFO, LILO, FILO, FIFO. Exam, that's another four-letter word, but I'm feeling like you guys are going to do just fine on that one. FIFO, first in, first out. That's how a queue works. We go to the grocery store and the cashier opens up a new line. You get there first, I get there next, and that other guy gets there behind me. Guess who's going to get serviced first? You are, then me, then that other guy. That's the way it works. First in is the first one to be served. A stack works using the blank principle. So we've got all those letters again. How's this going to work? In order to answer this, this is one of these that you need to be thinking and remember. Okay, well, what is a stack? A stack is like a stack of pancakes. As we throw the pancakes on top of each other, the last one that goes on is also going to be the first one that comes out. So it's last in, first out. It's a really kind of inefficient for our pancakes because you're constantly serving the freshest pancakes. You're not rotating your inventory. You'd want to rotate and throw out the oldest one to the next. But it works great for an undo operation. If you look at your website, your browser history, you want to hit back, 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 back. That's how a stack works. It's going to look and say, oh, well, what was the last website you visited? Pop it off for you so that you can have that. How about a set? A set ADT allows duplicate items, true or false. A set does not. What does a bag? A bag and a set are kind of similar. It's you're just kind of throwing everything into a collection, into well, kind of like a bag. You're playing Scrabble. You're throwing all of your letters into the bag. The difference is a set's only going to let you have one of each letter. A bag is going to let you have multiples. In fact, if you are working with this and you have a bag filled with duplicates and you're like, I really didn't want any duplicates, you can just cast it into a set and the set's just going to drop all of your duplicates out for you. Okay, nice. How about this? A queue and a deck use the same operation, same Python operations. When you take your exam, you need to know these Python operations. This course is built on top of Python knowledge. You need to have some basic Python knowledge. And as you prepare to take the exam, you need to be thinking about, okay, a queue, how am I going to add an element? How am I going to remove an element? How am I going to, if I'm working with an array and I want to insert an element or remove at something like that, you should be familiar with those so that you can have those readily available to get on your multiple choice exam. Queue and a deck do not have the same operation. Remember, a deck, by the way, is DQ, double-ended queue. In fact, I had that spelled wrong. It should not say double-end. It should not say DQ. It should say DEQUE. That is your deck. A queue. How do we add to that? A deck. How do we remove that? You want to remember with your deck, you've got push front, push back, pop front, pop back. So you don't have to worry about that with a queue, because a queue always is adding uh, to the back, servicing the front. With our deck, you have to specify, are you working with the front? Or are you working with the back? So you have to have that uh, in your mind. All right, so select all stack operations. Give you lots of time on this question. I'm not sure why. You're not going to need it, I feel certain. Peek, push, and pop. Keep in mind the difference between peek and pop. When we use pop, we are actually pulling that pancake off and we're eating it. When we peek, we're just looking at it. We're deciding if we're gonna eat it, and we're just evaluating it, but we haven't taken it off. So that's your difference between pop and peek. Janelle, you've got the highest answer streak, and you're not even on the leaderboard. I expect to see you pop up here. All right, so now we're going to think about this. This is something that I could see being on the objective assessment. So we have, given my stack, 3 is on top and 2. So you've got 3 on top, 3 on top, 2 on the bottom. You're going to push 5, peek, pop, pop is the new stack. Just think about this. I'll just keep talking to make it more difficult for you. You are allowed to have a whiteboard when you take the exam. It is not a bad idea to have available. Get a question like this to just be able to do a quick little visualization, write this down, 3 and 2. Okay, what happens when I do push 5? What happens when I peek? What happens when I pop, pop? Okay, vast majority of you did get this right. So we had 3 and 2, 3, 3 and 2. We push 5. What does that mean? That means we now have 5, 3, and 2. We peak. Does that change anything? No, it does not. We pop. What does that do? Well, that puts us back to 3 and 2. We pop again. What does that do? That brings us back down to just 2. And that's what the answer said. So I did that right. Good. Yeah, don't be ashamed to bring that out. And you have fingers and toes. Don't be afraid to use those fingers and toes as you're trying to keep track of things, especially the algorithm and things with loops. Doubly linked lists contain what items do you think? So linked lists are all about nodes and pointers. Of course, I'm not going to help if you don't have data inside of those. But that's it. Remember, if you've got a doubly linked list, then you've got to be pointing to the previous and the next and your data. So what else are you going to see on that? You're also going to see head and tail. So plenty of things to keep in mind for that. You want to make sure that you understand how to actually how things are actually happening when you add a pointer. The process of adding something in, say, the middle of your linked list. How do you actually do that versus if you're working with an array? It really kind of helps to bring the whole idea of data structures and algorithms together. You want to see why that makes a difference. Why do we even care what our underlying data structure is on our abstract data types? That is key. That's really a key point for this course. Which statement is not executed when a new node is appended to linked list mylist? When we are saying appending to the list, by default, appending to the list means you're just adding it to the end. We said prepending, that means we'd be putting it at the front, but we're appending it, so we're just adding something to the end of your list, of your linked list, rather. Yeah, yeah, we're not worried about the head. We don't have to worry about the head at all because we're only working with the end of the list. So nice and easy breezy. We're just going to do the list tail. Next will be the new node, and then say that, hey, the tail now equals that new node. Good work. A couple questions left for you here about graphs. Graphs are composed of the following two elements. Graphs, another one that I would love to give you plenty of questions on this objective assessment. There are plenty of vocabulary terms and just great concepts. And graphs are one of the most common uh, algorithms that we're going to be working with. We use them daily if we're driving. You have vertices and edges. Do you know which is which? You definitely should. All right, last question. Done great. I've enjoyed working with you. Thanks for being here today. So this final question says, in a weighted graph, values are assigned to vertices. True or false question? The answer is false. Why? Where are they assigned to? They're assigned to edges. They're assigned to the edges. The edges are the actual pointers. All right, so there is our podium, and you all did great. So thanks for joining me.